Wait, wait. Where do you get the link? Oh, share. God.
Okay, did you start streaming? Okay, please. Rishi, can you share the link with me? Share the YouTube link with me.
Okay. Yeah, how is that?
Yes, that works.
Okay, I'm just. I do it as a standard PDF, yeah, right? The presentation.
Yes, get it as a standard PDF.
Okay. Yeah, what's up? I'll have to.
Also, guys, by the way, did you use any data sets? Uh, if you used any external data sets, then send it to me.
Both of these, I'll give IIT Madras access, yeah? Like the notebooks.
Yep.
Yeah, just see if this is working.
Yes, yours works. Atreya, send your presentation as a PDF or give me access. You can give me access to view or download. Be better if you download it and send it to me as a PDF.
Okay, sure.
Yeah, I think this is the PDF version.
Neela, don't worry, I can download yours.
Hmm.
Srikar, um, if I share
Uh-huh.
this with you, will you be able to download? Because I don't have Canva Pro.
Yes, yes. Okay, no, I can't download.
Okay, but then you're able to download Neera's, right?
Just download as PDF, no?
Send it.
Fine.
Yeah, I'm trying to download as PDF too. Um, is this upgrade to Canva for Teams?
Fine.
Oh,
Send it to me.
oh,
I'll figure it out. Give me edit access
okay.
and send it to me. I'll figure it out.
Yes. 138, right?
Yes.
Yeah. Okay, yeah. I have shared this with you.
We'll start the session in 5 minutes time. If you have any of your friends yet to join, ask them to join. Although session notebook, session resources are already uploaded to the GitHub repository, you can check it out there. Uh, One thing in mind for this session is up until now, you have only done analytics of data. This is the first time you'll be introduced to neural networks. This is completely new. Even if you didn't understand some of the parts from the previous session, don't worry. From here onwards, it will be like a new chapter. And yes, we will start in 5 minutes time. Atreya, you can start. We will start with the session.
Okay, sure. Um, Hello, guys. Hello, everyone. Welcome to the AI Club Summer School Session 5 on Introduction to Deep Learning. Today, we will start with a brief overview of what deep learning is. So here, let's start off. Um, okay. So, the first question that needs to be that one thinks of is what is deep learning? And don't worry, it's not that deep. Uh, I think by the end of the session, uh, let's look at what our goal is. So, the goal for today's session is to understand why deep learning is better than conventional machine learning models. We'll go through each of these very carefully. We'll go through the fundamentals of what makes up a neural network, and we'll also go over an implementation of a neural network. Okay. So first, what is deep learning? So deep learning, the definition says that it is a type of machine learning where multiple layers of processing are used to extract progressively higher level features from data. Okay, so let's break that down. So essentially, what this is telling us is that data, as we all know, has patterns. And the goal of data science is to analyze these patterns and exploit these patterns. So, for example, the basis of all of data science is the underlying trust that even seemingly random occurrences in the real world have a complex pattern inside them. The purpose of all that we are learning here is to try to recognize those patterns, exploit them, and make useful predictions about the future, right? So that's the goal of what we're trying to do. So what deep learning is actually doing is that it's using multiple layers of processing. We'll get into what those layers are and how we can design those layers to better process data. But at the end of the day, multiple layers are being used to process data so that the layers can extract higher level features from the data. So features are characteristics of the data that is unique to it. So features are really what helps us distinguish one data from a data point which is of a different class. So what do I mean by that? Um, so let's go here. So early solutions. So let's consider classification task. So what is a classification task? It's we are given a bunch of images, and our job is to classify the ones that we are asked to classify. Let's think that through with a conventional example. So I would like you to consider these four images that you see here on the screen, and really just take a moment to appreciate uh, how powerful, how brilliant our brain is, such that it can recognize these three images as motorcycles, which they are, and one below is a car. So let's now imagine yourself as as a computer scientist sitting in some lab, and you're trying to get this computer to recognize what an image is the image if given an image, is it the image of a motorcycle or is it the image of a car? So now try to appreciate how brilliant that our brain can do this so easily, and yet it appears a very daunting task when you're trying to actually make your computer try to understand what this is. So look at that. So you may think, okay, maybe I can point out to the computer certain elements of a motorcycle that it should look out for, right? And if those elements are there in the image, then the computer should classify the image as a motorcycle. That makes sense. So now let's try to find those elements. Those elements are in fact what are called features. So let's find those features. Maybe okay, so you look at the motorcycle image and you see, oh my god, okay, it has two tires. So okay, do you think tires are therefore what helps a computer distinguish a motorcycle from a car? Well, no, because you see two tires here as well in the image of the car. Okay, what about the color of the vehicle? So this motorcycle is yellow, right? It has a yellow paint. But so does this car. So that is not helping you distinguish the motorcycle against the car as well. What about the orientation? You can see that this motorcycle is facing the left, this motorcycle is facing the right, and this third motorcycle is facing at a weird angle that you know that your eyes are telling you that it's pointing somewhat towards your right, but towards you, right? And now your task seems to be more hopeless, right? I mean, all of these images are motorcycles, but they have different orientations, different colors, different different ways that they're different lighting, and almost everything about their pixel values are different. How on earth would you find features that are exactly common to these images, but exactly give you a negative test for the image of a car because that's what you want to do, right? So that is a problem that we face. So the issue is that it's quite hard to find meaningful features in an image. That is, the feature that should remain the same when irrelevant changes are made to the image. So what do I mean by irrelevant? Irrelevant changes are changes like if the motorcycle were to be five, say, 7 pixels to the right, or 7, 8 pixels to the top, or maybe it's sort of enlarged, or maybe it's rotated by 30 degrees. All of those are irrelevant because they still ensure that the image is still a motorcycle. But the feature should change when relevant changes are made. As in, maybe the two wheels are made into four wheels. In that case, it's no longer a motorcycle, it's a car, right? So that kind of feature extraction is quite hard. And so that is a problem with conventional machine learning models, right? Okay, now let's examine another problem with conventional models, that is scalability. So let's think about it. You have some data. Okay, so you have, let's say you have a sibling, let's say a sister. So your sister goes to school. Maybe she goes to school early 3 days of the week and late 4 days of the week. Um, so that's some data that you have. Okay, and let's say you can run a classification algorithm with this. Okay, so you make a model and you're able to make some intelligent predictions out of this. It would make sense that if you had more data, let's say twice the data, your model would approximately be equally that better, right? The more data that you have, your prediction, it seems intuitive to assume that your prediction will be equally better. But the issue with conventional problems, that is the models that you've seen so far, the issue with them is that after a while, after a certain amount of data, they begin to saturate. That is, with additional data, their performance does not increase or it increases negligibly. So that is something that you don't like, right? I mean, imagine if you had a very powerful supercomputer and you had tons and tons of data, you'd like your model to be very, very, very accurate, right? That is the goal of what we are trying to do. But classical machine learning algorithms, which are non-deep. So we're going to get into what deep is exactly. So non-deep algorithms begin to saturate. Okay. So now deep learning. So what is deep learning, right? Deep learning is based on this one principle. Okay, so this is the algorithm, that's this hypothesis that brought about the idea of that such a thing like deep learning can exist. So as we've been discussing in the previous few slides, the majority of the work done in any machine learning lab or something was only feature extraction. That is, how can we represent a given image in a unique feature vector such that only similar images give a positive test and all others give a negative test, right? As we've discussed multiple times, this is what a feature means. So tens and thousands of researchers would sit and extract features from data, and this had to be done for all types of classification, right? Because think of unique features in an image of a plant, as you can see here, right? It makes sense that the features of this image would be quite different from the features needed to extract the image of a motorcycle. So each image would need a different processing style altogether, right? So that is a big task. It's a big pain for you to do this for lots and lots of images. And we humans are not quite good at doing rigorous work for a monotonous work for a long time. So we try to find ways to automated, right? So that's what we are trying to do here. So again, so this flowchart should represent all the thought process in one line. You have an image. You represent its essential qualities. The pixels are definitely not the essential qualities because, as you've seen in the previous example, they can be pretty random while the image remains the same, right? So the goal here is to represent its essential qualities as a feature vector, and you plug in these essential qualities into a standard linear regression model, something you may have done in the previous session. But again, I've told you guys that this session will be completely independent, so I'm not going to assume that you know anything about any regression model. Okay, that's completely fine. Okay, so I would like you to guys to scan this QR code for some time. I'll leave this open here. So scan this QR, please. Uh, I will ask you one question just to make sure that we are all on the same page. Um, so yeah, can you guys try and answer this question? I'll keep this QR code open for a little while uh, for you guys to scan. I'll keep it open for a minute or so maybe. Um, and you guys can also take this minute to maybe process a bit of what I've just said about features, how feature extraction is painful, and what we are trying to do is eliminate the human involvement from this, right? So think about that, and then do answer this question. Oh, yeah. Can you guys? I'll show the results. You're unable to see the question. Okay. Yeah, you're right. I'm also facing a little problem. Let's. Huh. Okay, give me 1 second. Okay, give me 1 second, guys. I think I'm facing a network issue. Okay. How about now? Are you guys able to are you guys able to see the question now? Okay. Uh, how about now? Are you guys able to see the question? Are you guys able to hear me? Uh, can someone confirm that my voice is audible?
Yes, you're audible.
Okay. I think I'm having a small internet problem. Don't worry. I think I'll fix it in a minute or so.
Maybe stop sharing and try resharing again.
Okay. Sure. Are you guys able to see my screen now?
Yes.
All right. Okay. How about now? Are you guys able to scan? Are you able to see the question?
Yes.
Okay. Okay. Great. The majority of I'll give a couple of seconds. Okay. I'll give a half a minute for you guys to answer this question. So yeah, I think the general way I just want you to think about it is that this isn't a hard topic. It'll get a little bit mathematical towards the end, but keep this intuition in mind, guys. Okay, keep what we're trying to do here. At every stage, imagine yourselves as a data scientist. Imagine yourself as somebody building these things, somebody inventing these things, and try to see why you would have thought of something in the first place. Okay, imagine you were in the 1960s or so. Imagine how you would have invented something that would have resulted in what there is today. Okay, so that is okay. I think we have a decent number of responses. So I'll just uh, show the right. So right. So yeah, the answer is both A and B. I suppose the options A and B are sort of mixed up, so it's difficult to say. But right, so as I've talked about, scalability is an issue with non-deep machine learning models. And the second thing is that it automates feature recognition, right? That's what we've been talking about. Deep learning does usually, conventionally, a lot of data is plugged into deep learning, but that is not a necessity, and it's not an advantage per se, either, right? So I think that's all right. So let's move on. Uh, all right. So, okay, what is the neural network? So now we'll really get into what actual deep learning is. So, what is a neural network? So let's examine both those words separately. So, what is a neuron, and how are they connected? Right? What's the network? So here I have an image of a neuron. It's a biological neuron. Something I think it was studied in biology in class in eighth grade or so. These are dendrites, that is parts of the neuron where input signals are received. Here is the axon, which is the main body of the neuron. I mean, and here are the nerve endings. The nerve endings are uh, the where the neuron sends out a signal. So we are trying to model this neuron, in our own sense. So you can think of a neuron in two ways: something that takes in a bunch of inputs and sends out an output. Okay. If you're familiar with calculus, then this is what a function does. So a function has a bunch of inputs and it gives you one output. That's it. That's all a function is. But in case you're not familiar with what a function is, no worries. You can think of this as an empty box which can contain a number, specifically a number between 0 and 1. Okay. So this number is called its activation, and we'll be using the word activation more often. So I want you guys to keep that in mind. Okay. So forget all of this biological complexity. Right now, a neuron is just a box, and that box has a number in it. Okay. Um. Okay. So, what is the use of this box? So now we'll look into how these boxes are connected. So how are the neurons connected? So these neurons must somehow work together to mimic human discrimination. That is, we want these neurons to all, to interact with each other properly. You want them to communicate information well, so that they can give you meaningful results, right? So now, an intuitive way you might think of transfer of information is that some information is automatically more important than other information, right? For example, some information say tomorrow is a holiday for your college or school. That seems to be more important information than something uh, you know something like uh, something, unfortunately, all the examples in my head are happen to be quite important. But yeah, so information clearly has different weightages, right? So you'd want to assign a weight to a certain transfer of information. So some connections are more important than others, so they're associated each a weight. So so before we get into all of this, I just like to show you how a neural network looks like. Okay, so this is a general representation of a neural network. Each of the circles you see, they are neurons. They contain a number. Each of those lines you see are connections between the neurons such that meaningful transfer of information can take place. Each of these connections are associated with a weight. That is how important the connection between these two neurons is. So, for example, if you consider this neuron and this neuron, if that information transfer is very, very important, then that weight is going to be high. It's going to be some 12 or 13 or so, just as an example. Whereas sort of an irrelevant information may have a weight of zero point 0.1 or zero point 0.3. Things can also have negative weights. I just want you to know that too. Things can have like weights of -12 or so if it's very important, but in a different sense of way. So now we'll actually come into what weights are and what biases are. So there are a few more things to look in there. So to be more concrete, a neuron has multiple inputs coming in. Remember, I told you about dendrites in this image of a neuron. I told you that there are multiple input signals coming in. So the way we look into what that is that it has multiple new inputs, and each of those inputs again has a weight, right? That's what we have seen in the diagram of the neural network. Each input has a weight of the connection. So let's say that connection is Wi. Okay, is I because there are multiple connections, right? So there could be multiple inputs. Each input, let's denote it by xi. I is a subscript. So xi is, as you can see here, is an input, and wi is the weight associated with that input. So what you do is you multiply the weight and that input, and you add together all the given inputs. Okay. Once you do that, that is just simply your, as of now, that is what the output of the neuron is. So it just takes in a bunch of inputs, it computes the weighted sum, and it spits out that number as the output. However, sometimes some different parameters, where you're dealing with different parameters in data, you may want to associate each of them with a different weight. This is not the same weight used in the communication of two neurons, rather in the activation of one neuron itself. By the way, revising, activation means the number that which the neuron has holds, basically. So you want to distinguish different activations, because different information may have different priority, different importance levels, right? So you add something called a bias. So you add one number to this weighted sum. Okay, what is this f of sitting outside, right? So as of now, I want you to kind of ignore that, but just know that it is some transformation that we are going to do to this entire sum, so that it has some nice properties. Okay. I'll just tell you what it is. So those functions that you see outside are called activation functions. So so there are two reasons why we'd want to use activation functions. I won't tell you what they are immediately because they require a little bit mathematics. But so we want one reason is that we want to keep these calculations from exploding. So what do I mean by that? So well, these weights can be any numbers. I've told you that the inputs are generally between 0 and 1. So this weighted sum can be some big number if with appropriate values of weights and so on, because this is an addition, right? This is a summation. If you add a bias, again that can be any other number as well. Now, if this is the output of this neuron, you know that in a neural network, the output of a neuron is going to be the input of another neuron, right? That's what the neural network is. So imagine now computing the weighted sum of this output and some other weights. You can clearly imagine that this iterative process is going to give you larger and larger numbers. It could, right? So it could give you larger and larger numbers and until it sort of explodes. And you don't want to do that, right? So you'd like to keep it within a bound. You'd like to keep all these activations between in a certain limit. So that is one reason. Another reason is that this linear sum is a linear combination, right? And this is a little more abstract, so I won't get into it much. But the effective complexity of this is going to be linear. For you to digest more non-linear or more complicated aspects of data, you would like to introduce a certain degree of non-linearity. That is another reason we'd like to use an activation function. There are three types of activation functions. We'll see what all these are when we go to the implementation as well. But I'll just tell you what they are right now. You have sigmoidal activation, or you have a hyperbolic tangent, or you have a ReLU. It's called rectified linear unit activation. So this is I've just shown you what a sigmoidal function. This is sigmoid. Sigmoid is just a function. It's one over one plus e to the negative x. And so what you do is when you have the weighted sum plus the bias, you just put it into this sigmoid and you compute the value. Okay. So yeah, so that's what sigmoid is. Nowadays, sigmoid isn't very extensively used. What is extensively used is ReLU, because ReLU gives actually the fastest results. I'll tell you, ReLU is basically if your weighted sum plus the bias happens to be negative, then the ReLU just makes it zero. Otherwise, it keeps it as it is. So that's what the rectified linear unit activation is. Um, it also solves a vanishing gradient problem. I will not tell you what that is right now because we don't yet know what the gradient is, but we'll come back to that later. Okay, so right now I think you have a general overview of what an activation function is, what weights and what biases are, and how a general neural network is structured. So now you can see why we would like to structure it this way. All the weights are like this, right? They're connected here. You see that the input layer is going to represent the input pixels, right? The image is going to be plugged in through here, and your hidden layer. So okay, I'll get into what these are. So this so every neural network has an input and output layer. That should be intuitive, right? You have the input image. The output image will tell you what the neural network thinks the classes. Like let's say you have a classification problem between the motorcycle and a car, right? Like the example that we just saw. So you would have two output layers. One neuron representing the network's opinion or the probability of it being a motorcycle. The second neuron being the network's opinion of the image being a car. So if the first neuron had some activation of zero point 0.7 and the second one had an activation of zero point 0.3, then you would know that the network's opinion of the image is that it is a motorcycle. That's what the output layer tells you. The input layer is simply the values of all the pixels of the image. So what would you like this hidden layer to do? So these hidden layers, you would expect that it's going to take some of the important features of this image. So, well, let's say you're given the image of a motorcycle. Maybe the first hidden layer will learn to recognize the fact that there are two tires. Maybe the second hidden layer will try to recognize that there is a sort of a connecting bar in between that represents the body of the motorcycle. Maybe the third layer is telling you what then it maybe if it has an exhaust pipe or something. Okay. Of course, I'm just this is at a very basic level. The idea is not to just simply recognize different parts of the image, rather to recognize more abstract versions of the same data. What do I mean by abstract? As in things which we cannot directly, uh, things which we cannot see on our own when we look at the image, but the network can learn very cleverly. So when you have the final hidden layer, we'd expect it to have a very abstract understanding of this data. And output layer will simply combine this knowledge appropriately. That is, maybe the first neuron will contain how some sense of motorcycleness of the image, and the output layer will simply have a very strong weight connected to it. Then you'd know that this neuron will fire most likely when this input seems to be quite big, right? If this is somewhere around 0.9 and this weight is quite heavy, like 12 or so, then this neuron will activate a lot. Whereas if some neuron here describing the carness of the image, that is how much of the image it appears to be a car, then if that has a very strong weight towards the neuron, depicting the output of a car, then the activation of this neuron would tell the neural network that, oh god, this is probably a car, right? That is the way it works. Okay. So until now we have seen what a neural network is. So now we are going to get into how it actually works. So how do we design this neural network to actually do what we want it to do? So we want, so this is another different neural network. It has two neurons in its first layer, in the input layer. It has four neurons in the hidden layer, and it has one neuron in the output layer. Okay. So we want information to dissolve into its most basic components. It is these features which truly distinguish some image from another, some class from another class. So these weights dictate what neurons are activated more depending upon the input, right? So depending on what neurons show more activation, the weights will ensure that that neuron is given, according priority, right? Priority accordingly. This is called a forward path because as the green arrow indicates, you're going forward. You're pushing the data on one end, on the left end, and you're getting your output on the right end. And at each time, you're progressively going towards the right? You're progressively moving the data forward, and these hidden layers are going to extract the more abstract versions of the data, and this output is going to combine these abstract features and give you an output. Okay, so this is called a forward pass. So again, I think I've already described this. So say we want to recognize an image. Each image has pixels which contain values that dictate how bright the pixel is, right? So if you say it's grayscale, then you will be rid of all that red, blue, green complexity. So let's say it's grayscale. So if the image of the pixel value is 0, then we say it's black. If it's 1, it's white. Okay, so anywhere in between dictates how white it is. So the output that we get will be in the form of each neuron having a certain value. And it's quite intuitive to say that the neuron with the greatest value is the network's opinion of what class the image belongs to, right? So uh, if the if you are so if let's say you're trying to as we shall later see, and as Nilavo will continue, Nilavo is also going to take the session after me. uh, as he will continue, we'll take the example of recognizing handwritten digits. Okay, so the job of our model is to recognize handwritten digits, and handwritten digits are there's a data set available, a public data set called MNIST. Okay, uh, the MNIST data set has basically tuples of an image and its corresponding real value. So it has a fixed image of a 7 written, and then it has the actual digit 7 type next to it. So that's the data point that we have, right? So that's the handwritten 7 has 784 pixels, as we shall see, and each pixel has a value indicating how bright it is, and all those pixels together make up the handwritten digit 7. And our network should somehow classify this digit as 7. So if if the so in this case, it seems intuitive to say that the output neurons, we should have 10 output neurons, right? So we should have output neurons, each corresponding to the digit 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And if the activation of the neuron 7 happens to be something like 0.6 or something quite high, then the network clearly thinks that 7 is the handwritten digit. So that is what the network's opinion of the answer is. Okay, but there's an issue right now. Since all our weights and biases are just random values, we haven't done anything, right? These are just random numbers at this point. Since all the weights and biases, by the way, whenever I talk about parameters of the network, I just mean the weights and the biases. Okay. Since they're all random, we expect a random outcome. We expect some random neuron to give you some random value, right? Some which is of no use to anyone. So now we're just looking at how we can improve. Okay. So now I'll show you a little bit of mathematics. Okay, as in a little bit of notation. There's no need to get scared here because the underlying concept is very, very simple. It's just that the math makes it looks pretty hard. But every neuron, the activation of every neuron is represented by the small letter A. Okay, I think that is something to keep in mind. The superscript of every neuron is enclosed in a circular bracket, and that represents the layer number of the neuron. It is not the exponent. Okay, you're not exponentiating anything. The zero just means that this is the zeroth layer. Okay, as you can see in the green arrow represents the zeroth layer, the input layer. The first layer is the hidden layer, and the second layer is the output layer. As you can see, the number that is enclosed within the circular bracket represents the layer of the neuron. The subscript to the neuron represents what the neuron is, the label of the neuron. So the input layer has two neurons, right? So it has A0 and A1. It has a superscript of 0 because it is the zeroth layer. Similarly, the hidden layer has A01 is A11, A21, and A31 because there are 0, 1, 2, and 3 neurons in the second layer. The output layer has only one neuron, so it's simply A0, but the superscript is 2 because it is a second layer. Okay. Now we'll move on to what the weight is. So you see this W here, that is the weight. Okay. The weight is basically the arrow, right? It's the number that depicts the strength and the connection between these two neurons. So I want you to keep in mind that whenever a weight is connecting a layer 0 to a layer 1, you depict by convention the weight as with a layer 1. Okay. So this is called weight with a layer 1 or between what two neurons. So you can clearly see that it is the weight connects the neurons 0 and the neuron 2 here, right? So you write 2 0. So it's a little opposite, right? You think that you would write this as weight 0 2 because it's connecting 0 to 2, but actually you would write 2 0 because the notation is simply you'll see this later when we try to represent this entire thing in the form of a matrix. There's no need to get ahead of ourselves, but this is the convention. Okay, so you represent any weight connecting a J and a K neuron as WKJ. Okay, and you represent the layer of that weight as the layer of the succeeding weight, succeeding neuron. Sorry. So these are the equations representing what I've already told you. It just seems complicated, but if you notice very carefully, the first part is simply the weighted sum, right? It is just you take the activation of this neuron, multiply it with this weight, take the activation of the second neuron, multiply it with that weight, and add a bias. That's it. And similarly, do the process for other four things. Okay, I just leave it on the screen for a little while for you to get used to what this equation is. I hope it's clear. It seems quite hard, yes, but it's just a simple weighted sum, and you add a bias. Similarly, it's the same process that you do for the output layer. The output layer A02 is simply A10, which is this neuron times this weight, plus this neuron times this weight, plus the activation of this neuron times this weight, plus the activation of this neuron times this weight, plus a bias. So, of course, there is an activation function applied to each of these neurons at their outputs, but I have not chosen to represent that because, as you can already see, this seems pretty complicated even without the activation function. Not to worry, the activation function is just simply a sort of a transformation applied at the very end. Conceptually, this is the majority of what it is. Okay. Now, where does the learning come in? Okay. By the way, have you guys recognized why this is called deep learning? What is deep about it? So, what is deep is actually the fact that there are multiple layers. So, the deepness. Why do you call this deep learning? It's because there are multiple layers which will learn this image, the features of the image, right? Whereas non-deep models don't have this multiple abstraction generators, right? That is why it is called deep learning. Okay, but what about learning? Where is the learning coming in, right? What is learning? So let's go into that now. Okay, so the forward pass until now, what you've seen, the forward pass is basically what a baby does, right? Random actions which seem childish, right? Okay, I suppose that is where the phrase comes from, childish, because that's what a child does. But But we also know that over time we learn, right? We don't put our hand into the fire anymore because we just know that if we do so, we'll get hurt, and that is not something that we want to do. So where did this entire process of learning come in, right? Initially, when we were a bee, we were experimental, like we were trying to do everything and trying to learn. So now I think that's an intuitive way of understanding what learning is, right? So uh, so we are now going to go into arguably the most important part of a neural network. Until now, just to recap, we have covered what a neural network is, what weights and what biases are, and what activation functions are. Though I have not told you what the vanishing gradient problem is, neither have I gone into depth. That's because we'll come back to that later. But we've also seen what a forward pass is. A forward pass is nothing but a forward propagation of information. That is, from the input, the model predicts an output. As of now, because our weights and biases are random, it's its the output is random too. But we are trying to fix that. So right now, scan this QR code, guys. While you soak all of that knowledge in, scan this QR code to mark your attendance for the session. I'll leave it on for a little while. Maybe I'll leave it on for a minute or two. Are you able to scan? Can someone confirm that is this working? Can someone confirm whether the QR code is working? Um, okay. Uh, all right. Okay. Then can the moderators or somebody? Okay. Fine. All right.
Atreya?
Okay. Yes.
Yeah, also can you take up some questions from the Q&A section?
Okay. Sure. I'll be doing that. Meanwhile, if you guys could fix the fix the QR code. My bad.
Okay, yeah. We'll fix that also. All right.
Sure. I'll take the Q&A now.
I guess there are not many
Um,
doubts in the Q&A. There are some possibly one or two questions
okay.
only. So you can quickly
Sure.
take
Okay.
them up and then you
Yes.
can continue.
I'm okay. In what scene is deep learning different from machine learning? Very good question. It is not. Deep learning is a subset of machine learning. So that is something, it's a common misconception. Deep learning is a subset of machine learning. It is uh, deep learning. It's simply, as I said, it's a type of machine learning where you abstract the features, right? You automate the process of feature abstraction instead of trying to do it by yourself, right? So that is what it is. Does the B plus X times W come from a regression model? Yes, you are right. That is true. That is, I think that might have already been covered in the previous session, but I've deliberately chosen to repeat it again because we have told you guys that this is going to be a completely new and independent session, right? So yeah, that's true. Okay. Uh, what is a significant use of ReLU? Okay, so yes, as I mentioned, ReLU is very extensively used. It's used to introduce non-linearity. So what would otherwise be, as I've talked about, um, linear combinations alone can only produce, linear combinations, right? So you would like to introduce a bit of complexity so that the ML model, so that the deep learning model can learn better. So we'll come back to what learning is exactly because we haven't talked about what backward passes are. we have not talked about gradient descent and so on, right? So once we understand what a gradient is and so on, we'll come back to activation functions and examine them better. Okay. W20. Oh yeah, what I just mean is that if you're connecting the zeroth neuron of the uh, zeroth layer and the second neuron of the first layer, you don't denote the weight as W02. You denote it as W20. Okay, that's all I mean. It's just a notation. It is basically telling the notation is telling you what two neurons the weight is connecting. Okay, that's it. I think that those are all the doubts. So also, how
Yeah,
are you
Atreya.
guys finding the session so far? Yes.
Okay, yeah. Before you go proceed, probably what you can do is unshare your screen once and download the QR code. I have shared it with you again. All right.
Okay.
And then
All right.
you can, it's up to you. You can show the QR code right now, and then you can continue with your session, or you can show the QR code at the end.
All right. Sure. Okay. Um. Okay. Yes, I will. Okay. I'll share the QR code at the end. What I will do is I'll share the QR code at the end,
If it's
and
convenient for you,
because
I can also like just share the attendance QR code. I'll just do that actually.
Okay, you can do that. That'll be easier, I guess.
Yeah, I'll just do that.
fine. Okay. Then should I?
This
Yeah, just a
this is
second,
the.
Atreya.
Yes.
I'll just keep this on for a minute and then I'll stop presenting.
Yeah, cool. So people, you can start scanning this QR code. Okay.
Again, guys, can you confirm that this is in fact the right attendance link?
Yeah, I'll verify. And also others, they can definitely react with a thumbs up if it works.
Yes.
Yeah, I guess this is the perfect one. All right.
Yeah. Okay, cool.
We'll wait for 1 more minute so that people can scan the QR code, and then Atreya, you can continue.
Okay. Sure.
Okay. Okay, I guess there is another issue. Can you guys hold for a minute? I guess it is asking for access.
Okay.
1 minute. I'll fix that.
Okay. So yeah, while you guys wait, just think about um, what how we'll try to get a sense of what the error is. Okay, so we have something that is predicting some random things. We know what it should be doing, but we know that it is not doing that. So let's so we will be looking in the future once this attendance issue is over. We will be looking at how we're going to get a measure of how far off we are or how terrible our network is. Okay, so we'll be looking into that.
Yeah, guys, can you check now? I have updated the permission access. So now everyone should be able to scan and fill the form. If you can react with a thumbs up, or even if you can message in the WhatsApp groups, that should work. Okay, I see people saying problem solved. All right. We'll wait for 1 more minute. Okay. And then we'll continue.
Yes. Okay. All right. Okay.
And also adding to that, I guess again there are a few queries and few doubts about should MS Teams people fill or scan this QR code. As mentioned earlier, everyone should be scanning the QR code. So earlier we were having this policy only for the people attending on live stream, but right from session 3 or session 4, we have already mentioned even in the session saying that everyone attending the session should be scanning the QR code. Okay. So this is the only way in which we'll be taking attendance. And again, as mentioned earlier, we won't be sharing the GForm link in the YouTube chat or in the WhatsApp groups. The QR code will be shown only here to ensure that people who are attending the session can only get access to it. I hope that's clear. Fine. I guess Atreya, you can begin.
Yeah, I'll just stop
Okay.
sharing.
Okay.
Yes. Okay, I'll share my screen. I hope you guys can see the screen now. Can anyone confirm that?
Yep, your screen is
Yeah.
visible.
All right. Okay. So yes, as I have asked you guys to think about for a little bit, we'd like to measure for how bad our network is, right? Again, so what is our network doing? It's giving you an output based on all these weights and biases and activation function. After all of that, it's giving you an output. You know that the output. So currently, you're given that handwritten digit, as I've talked about previously. That handwritten digit 7 is actually a 7. You know that, right? That's the data set that's given to you. But let's say the neural network, because its weights and biases are all random. Let's say it is saying that it is 3. Okay. Let's say that the neuron corresponding to 3 has some activation of 0.97, which is quite high, right? So the neuron is pretty confidently saying that it's a 3, whereas it's not a 3, it's a 7. So the neuron is, that neural network is pretty bad right now, right? You want that to improve. So before you even try to think about how to improve, you have to think about how bad it is currently, right? You want an estimate of how bad it is currently. That is all the cost function is telling you. The cost function is a sense of how bad you are. Okay, how bad your network is. Sorry. So you have different ways to represent the error. Obviously, I mean there can be many ways to think about how many different forms of writing how bad our error is. So four common error loss functions are mean squared error, cross entropy loss, mean absolute error, hinge loss. This is not used much in deep learning. Okay, it's used in okay. As from amongst these four, I'm going to focus on mean square error only. Cross entropy loss. I'm not going to talk about all of these because these require little, prerequisites and what entropy is. For those familiar, entropy you may think of statistical entropy as negative p log p. Okay, but again, I'm not going to go into all of that. So we're just going to leave this. Just think about these are different forms of representing the cost function. The mean squared error is pretty intuitive and easy to understand. It is saying your output neuron here represented as a second layer. So let's say the neural network in this case has the two layers. The ith neuron has a certain activation, right? The y hat I is the actual value of what the ith neuron should be. So if the if the handwritten digit 7 is supposed to be a 7, then the neuron corresponding to 3 should ideally be 0. In fact, the neuron corresponding to any digit other than 7 should be 0, and the neuron corresponding to 7 should ideally be 1, right? So y hat will take those numbers 0, 0, 0, 0, 0, 0, 1, 0, 0, 0. Okay. And AI2 will just simply be what the outputs, the currently random outputs of the neurons. Okay. Why do you square? Again, I think this is a confusion that students may have had in their 11th or 12th grades while doing statistics and even later. In statistics, the square always seems to come up, in variance, standard deviation, and so on. I cannot answer very right now in detail yet, but just know that using absolute error, that is just finding out the difference, will make life harder for us because we'd like to do something called differentiating. So we'd like to calculate the gradient of this, and it turns out that the gradient of an absolute value is a kind of a pain because it is non-differentiable and so on. So we'd like to square to have a very nice, smooth kind of cost function. Why not, why don't you raise it to the power 4? That's a more difficult question. And, I'm not going to go into all of that yet. So, so again, just to revise, the cost function is not a function of our inputs. The cost function does not vary if we change our inputs. If we make the handwritten digit 7 as a handwritten digit of 5, the cost function shouldn't change. What should change? It should only change with respect to the weights and the biases, which are the parameters of the network. The output of the function is one real number, which indicates how badly the network is doing, okay, or how good if it's low. So the cost function, this is what the diagram of a cost function looks like. If the network has two parameters. So again, what do I mean by parameters? Again, think of them as weights and biases. So in this case, let's say the network has one weight and one bias. So that represents each of the two axes. The third axis, or the z-axis, represents the cost. So as you can see, if you consider this particular cost function at a very high value of a weight, so somewhere there, okay, outside the diagram, yeah, and somewhere around the high value of a bias, the cost is pretty high. So that's the way you would interpret this. So obviously, a network having only one weight and a bias is pretty ridiculous because in practice, you'll have tens of thousands, if not millions, of weights and biases. But it's very difficult to visualize a million dimensional graph, a million plus one dimensional graph. So we'll just visualize it in 3 dimensions. Okay. What's our goal here, though? The higher our cost function is, the worse our prediction is, right? That is, after all, what the cost function is telling us. It is telling us that if the cost is higher, our prediction is worse. This means that we want to minimize the cost function. The lower the cost function is, the closer that our model is to predicting the actual value, right? So since the cost function is a function of the weights and biases, this question, the above question here, is equivalent to asking, how can I change the weights and the biases of the network such that my cost function decreases? Minimum in the ideal case, right? If it's at the point B, so look at the point B, if the weights and the biases were all such that, the input space was at point B, then the cost function is at the lowest. That means your model is the most accurate. That is what you want. Okay, moving on. So first, now we are coming to the most important part of a neural network, which is the backward pass. So before we get into the mathematics, I'd like to talk a little bit about the intuition behind it. Because once you have the intuition, the mathematics, no matter how complicated it may seem, will actually turn out to be pretty simple, Okay, so consider this network here and consider this weight in particular. Okay, I want to talk about this weight. How does the value of this weight affect the cost function? Well, if you can't think of any way immediately, what do? Play around with it. That's after all what any of us as scientists should do. We should play around with something that we don't understand. So let's say we increase it a little bit. Is your cost function decreasing? Maybe it doesn't. Okay, so let us say that the weight was initially 4. I'm making up random numbers now. And let's say the cost function of the entire network happens to be 8. Okay, so if you want to see how this weight affects the cost function, make the weight from 4 to 4.1. If the cost becomes 8 to 8.5 or something, you know that this change in the weight is unfavorable because you ideally want to decrease the cost function, right? You want to make it the minimum. However, making this weight from 4 to 4.1 actually makes your cost from 8 to 8.5, which is not what you want. So what you actually do is you change the weight from 4 to say 3.9. So the intuition is you play around with each and every one of these weights. Such you increase it a little bit, decrease it a little bit, see what change is giving you a favorable change in the cost. And you incorporate all those changes in the network. If you keep incorporating this over and over again, you'll soon reach a setting of weights and biases such that the cost is the minimum, right? And that is what you want to do. That is all back propagation is. So if once you look at the mathematics and don't get scared because this is exactly the intuition behind it. Okay, now we'll actually go into the mathematics. So after we've gotten the intuition behind us, let's actually get down to the detail. After all, the beauty that lies in the detail, right? Okay, so ignore this mathematics on the left for now and focus on the right. A good way to find out how much the cost changes as a consequence of the change in a weight is given by the partial derivative. Okay, some of you may be unfamiliar with what a derivative is, but first note that what a partial derivative is nothing but a derivative. Just when you have multiple changes, the derivative takes on the form of different partial derivatives because the cost is dependent on multiple parameters, not just one, right? What is the derivative though? Uh, a simple way of explaining it is how much does a change in a given uh, parameter. So look at the now consider the left side. Look at dou c by dou w j k l minus one. Okay. Um, WJKL minus 1, as I have mentioned previously, is just the notation for a certain weight between the kth and the jth neuron of the L minus 2 and the L minus 1th layer, right? This dou C by dou W is just telling you how much does the cost change if I sort of play around with the weight a little bit. And with this weight alone, that is, if I keep all other weights in the network constant and I play with this weight alone, how much does the cost change? That is why you have a dou. In normal calculus, you'll have something called a D, right? DC by dW. But in this case, because cost is dependent on multiple parameters, you only measure the change with a certain weight while keeping the other weights constant. Okay, okay, this is all fine and nice for if the cost function is directly dependent on a certain weight. But what about indirect changes? Well, you have something called the chain rule in calculus. You don't need to worry much about it now. I'll simplify it a little bit later. But the chain rule is saying that the effects of an indirect thing on the cost can simply be written as a product of the effects of each direct influence. So I'll talk about what I mean by that. So this is using the chain rule. Now it seems pretty complicated, but I want you guys to focus on these three arrows here. Okay, these three arrows alone. Ignore everything else as of the moment, and notice that there's a nice cyclic pattern to this. So if you want to find out the change in the cost with respect to this weight, it is the same as finding the change in the cost with respect to something. So the activation of the zeroth neuron times the change in the activation of the zeroth neuron in the second layer with respect to the activation of the zeroth neuron in the first layer times the change in the activation of the zeroth neuron in the first layer with respect to the change in the weight of the zeroth neuron in the input and the first layers. Okay, that's a lot of things to process. But what you can think about is that each of these, right, each of these three arrows correspond to direct influences. That is, this weight between the Z input layer and the first layer directly influences this neuron, right? Doesn't it? Because this neuron is simply the weighted sum, right? And in that weighted sum, this weight plays a crucial factor. So this green arrow represents a direct change. That is, the influence can be easily measured. In fact, you see this green arrow on the left side. That is exactly how much that influence is. This the influence that this weight has on the next neuron is exactly the value of the previous neuron because the more the previous neuron is, the more the weighted sum is. After all, so that is what the effect of the change is. If you multiply all these indirect changes, then you direct changes, then you get the overall indirect change on the cost due to the weight functions. Okay, all of this may seem a little complicated right now. So we'll just skim through this. Okay, you'll understand it better once we actually go into what the algorithm for minimizing the cost function is, and that is called gradient descent. Okay, before we get into all of this, I would like to show you this image. So again, as you guys can see, this is a cost function, right? This is a cost function with two parameters, and a third axis is the cost. And this sort of surface is the cost versus the input, two inputs. This clearly looks like a kind of a hill, right? A valley, actually, right? Imagine So you start out with random weights and biases, right? That is like starting at a random point in the valley. Clearly, if you start at a random point in the valley, you would not expect to be at the bottom of the valley. You would expect to be somewhere in the slope of the mountain, right? You want to get to the bottom of the valley because that is what minimizing the cost function is about, right? So how would you do that? Physically, it makes sense that if you just let a ball, if you just release a ball from that point, it would come to the minimum, right? Because a ball, because of gravity and physics, it'll come to the minimum. Of course, there are a few asterisks that I put here. The asterisks are because ball has something called momentum, and we will not get into that. Gradient descent has something called no momentum. That is, you can see that it comes and just stops at the minimum here. A real ball wouldn't do that. But um, the idea is the same. You let a ball, you release a ball, and you follow its path through the hill and make sure it comes to the minimum. Okay, it's approximately like that. Let's not go into really what it is. There are more, of course. There are better optimizing algorithms than the gradient descent. Okay, but we will not get into that. Like stochastic gradient, RMS propagation, Adam. We'll not get into all of that. They're far more complicated than this question needs to be. Uh, the picture on the right is just telling you that this gradient is always perpendicular to the equi-level surfaces. So look at this is called a contour plot. What is saying is that these circles, these ellipses, as you can see on the picture, are points of the same level. That they're all at the same height from the ground. So you can see that this blue arrow, which is the gradient descent, whenever I talk about the gradient descent, I mean it's an algorithm. That is, it is a process that we perform to the weights and the biases to reach the minimum of the cost function. Okay. So the process, as you can see, is a time varying thing, right? Over time, it goes towards the minimum. That's what the process is doing. So this process always is perpendicular to the level surface. That's because it's trying to go in the steepest possible direction. Okay. Right. So now we'll come back to gradient descent. Okay. Uh, we can calculate the changes in the cost with respect to the changes in the weights and the biases, right? So we want to adjust the weights and the biases to kind of reduce the cost function. And the way we do that is it's theta j in this equation represent the parameters of the network, like weights and the biases. So the weights and the biases become the weights and the biases minus some factor times the gradient. This is called the gradient. The gradient is simply the collection of all the changes, individual changes in each parameter. So if you change the parameters negatively in this way, then the parameters will improve to a situation where the cost function decreases. Right? The direction of the steepest ascent of a function is given by its gradient. Since we want to descend in the steepest possible way, we proceed along the direction of the negative gradient. That's why you have a negative this. Okay. Of course, here I've taken this example is only for two parameters, theta naught and theta one. But in a network, as I mentioned, we'll have multiple parameters, usually millions. Okay. Okay. Now, what is alpha though? Okay, alpha seems to be something a little new. So alpha is something called a learning rate. It determines how fast or how much the updation of the weights and the biases are. If alpha is more, as you can see from this equation, theta j is going to get updated or it's going to increase or decrease by a large amount, right? Because this is a large amount then. If alpha is very small, in fact, if alpha is zero, then there is no updation at all, right? So if alpha is small, then its updation is slower. So these are the changes. If you have a small alpha, it will result in a slower convergence to the minimum. If you have a larger alpha, the issue is that it might overshoot the minimum and the cost function might actually start to increase after each iteration. So that is what alpha is. Alpha is actually a hyperparameter. I'll very briefly go into what a hyperparameter is. So think of you, you're designing a network here, right? You're designing a neural network. So you think of yourself as the god of this neural network. So you can change lots of things about the neural network. Like you can change how many neurons are there per layer. You can change how many hidden layers are there. You can change all of those things. The weights and biases will change by themselves depending on in all of them changing with goal to reduce the cost function. You can't change those, right? The learning rate is a hyperparameter. Hyperparameter are things which you as God can change. So you can change alpha. The network itself will not tell you what a good alpha is. You need to know that with various, lots of practice in data science as as a model maker and so on. So a good alpha is around generally 0.01. By practice, that's what you generally take. Okay, so now we'll just go into a code implementation. Okay, we'll see how this is. Okay, so I'll zoom in a little bit. Is this size okay? By the way, before that, is everybody okay? I mean, are there any questions? I think there might be a little bit. I have skimmed through the mathematical details of the gradient descent a little bit, right? But I will come back to this later if we have time after Neela's session. I don't want to take a time of his session. We're already at 6:15. I'll just briefly go through this. This is basically whatever we have described so far with a neural network. We are just trying to implement this in code. Okay. So this is a network implemented using PyTorch, which is an open source library. Neelavo will be talking more about PyTorch. I don't want to get into it. Just think of it as a library that we can access right now. Okay. So we are going to import PyTorch now. So while that's happening, so now we've imported PyTorch. Now we are going to initialize the parameters of the network. So again, remember what the parameters of the network are? They are the weights and the biases. As we have discussed, the parameters of the network comprise of the weights and biases. We initialize them randomly because, as you know, before we do anything, I mean, it's obviously random. Torch.rand does that. So x equals torch.rand 5, 1. So these are the inputs to the network. Okay, why are they random? That's because since we are trying to show you a very easy to use, easy to understand network. We don't want to use a very complicated data set and confuse you with all of that. So we just use a random input right now and a random output. What do I mean by a random output? I mean the actual value of what that input should correspond to. That is also random. 5, 1 represents the size of the input and output. 5, 1 just means that the input is of size 5. So there are 5 input neurons. Think about that. And the output, there are 2 output neurons. W1 is the first weight layer. C1 is the first bias of the first hidden layer. W2 is the weights corresponding to between the first and the second hidden layers. Z2 is the bias of the second hidden layer. W3 is the weights connecting the second hidden layer and the third output layer. Z3 is the bias of the output layer. Okay. So that's all done. Training the network. So now we are going to train. AT is simply used for matrix multiplication. Whenever you see an AT, think about it as multiplying two matrices. Okay, I suppose it's difficult to understand where matrices have come in. But if you remember this presentation, this part here, for those familiar with a little bit of linear algebra, know that these look a lot like linear equations. And linear equations can always be represented as a matrix, a matrix equation. So that's where the multiplication comes in. The multiplication comes in between the weights. The weights can be written as a matrix. The activations can also be written as a matrix. And this weighted sum is simply the product of two matrices. You add a vector of biases, and that gives you the vector of the next layer. Okay, but all of that is not required. So this is simply a forward pass. Forward pass simply means the forward propagation of information. So in this case, Y3, which is the output layer of the final output layer, is the forward propagation of all the information. So here X, see X here is the input vector. Those are the input qualities. W1 at X simply means that you're finding the weighted sum of all the inputs. Okay, that's what this is. You add a bias, Z1. You compute that weighted sum because you're going to go to the next layer. You add a bias to that. You add a sigmoidal activation. Remember, I told you what a sigmoidal activation is in brief. We didn't go over that in great detail, but that's okay. And then you again compute that weighted sum for the third layer, and you add the final bias. That is the output. What is the loss? This is the mean loss. Okay, it's the mean square loss, and this will tell you the cost of the uh, network. Okay, right now since all of our weights and biases are random, this cost is going to be some random thing. Okay, now you do something called back propagation. Okay, so remember we talked about what back propagation is. It is basically finding out how the weights and biases influence the cost and changing them appropriately to decrease the cost. So this is gradient descent. Don't worry about all the technicalities. Neelava will be going over those. But as you can clearly see that the weights are updated such that they decrease by some amount, which is called a learning rate. In this case, 0.005 times the gradient of W. The gradient simply means all the collection of the various changes in the cost with respect to all the weights in this case. Okay. Now you again do a forward pass. That is, with these new better weights and biases, better as in more suited to give you a less cost, you again forward propagate. That is, push the same information through the network and again compute the loss. So if we run this thing, what we expect is the cost should decrease because our model should get better, right? Because the weights and biases are getting better. Does that happen? Yep, it does. So it is initially 0.8 before the gradient descent. After one gradient descent step, it has decreased. So that's it. It's as simple as that. Perhaps this is not really telling you the true complexity in a neural network. It can only be understood when you're coding it from scratch. PyTorch really helps you with reducing lots of this thing. For example, remember we are in this presentation, this entire set of linear equations can simply be represented as one line in this one matrix product here, right? So PyTorch really simplifies it, and Neela will be going over in depth about how exactly it does that. But that's it. You have understood how to code a simple neural network, and this is all it is really. The concepts I think are I think it's intuitive to understand what every part of this is doing. Forward pass is basically you are pushing the information through to get an output. Back propagation is you calculate the error in the output and try to improve the next time you do it. That's it. It's like a baby trying to learn. That's it. That everything, every aspect of this is biologically inspired. So when a baby learns, it tries out something new, and then when a baby gets some sort of an error, right? As in how bad it is doing from either its parents or other means, and it tries to improve. So by the time you're an adult, it's likely that you're improved a lot and you won't do the things that you did when you were a baby, right? I mean, I still do things when I was a baby, but that's not the point. Yeah. So anyway, that is the point. I just like to go over this very briefly. I've not explained in depth at all. You can open this in your own devices and experiment with this. But I'm trying to show you how painful it is to actually build a neural network from scratch. Here, by using PyTorch, we have glossed over some very complicated things with just one line. But here we'll go over that in a little bit complexity. First, before anything, just look at how long the code is. So that is decently long, right? So that is long. That's exactly why we won't be going into this in great detail, but I'll just briefly explain. So here we're trying to build a neural network from scratch. And what is the purpose of the neural network? Well, as I've said before, we are trying to classify handwritten digits. So if we are given the image of a 5, we want to classify that as a 5. So we'll import the necessary library for that. Um, okay. So then, so here we are trying to load the MNIST data set. Okay, again, MNIST is simply the data set which will tell you which is yeah.
Yeah, I guess you need not go into the details. You can just very briefly run through.
Sure. Okay, yeah. Actually, you're right. I was thinking of wrapping up as well because it's 6:25. So okay. So basically, yeah, this is how it look like, and our task is to build this network which will classify this 100 digit. So briefly, you can see that we define activation functions. This is the structure of the neural network. These are all the weights and these are all the biases. This is forward propagation, right? This is forward propagation. You the first hidden layer, this is the second hidden layer, this is the third hidden layer, this is the output. At each stage, you apply a sigmoidal or you apply a softmax. Softmax. I don't think we have time to do what it is, but these are all different kinds of activation functions. And this is back propagation. Back propagation is a real pain. You can see, you remember all the theory that I went over in mathematics that I didn't go through in great detail because of this very reason. All the indirect changes can be calculated like this, and you'll have to multiply all of those. See here, you're calculating the indirect effect of the first and the second hidden layer on the overall cost. Then you update all the weights, update all the biases. This is basically gradient descent. You find the average cost over the entire batch, and then you print it. And you can see that, and you terminate the gradient descent after a certain number of steps. You can see that after a few iterations, after 10 iterations or so, the cost is slowly decreasing. Notice how it's 0.4609. Now it becomes 0.4603, 0.4598, and so on, until it comes to a sort of a minimum. So this is basically what a neural network is. And then you finally test the model with another final forward pass, given an image. You compare it with a certain image and you calculate the accuracy of the network. This is all deep learning. This is all artificial intelligence is based on. So now, congratulations. I think you have learned how to the intuition behind a neural network and the intuition behind a neural network and a very brief sense of how it's coded. I think I've gone on with a certain detail the PyTorch implementation, but the NumPy implementation I've skimmed over pretty much because it takes a lot of time to explain and it's pretty mathematically very gory. So yes, I think we're out of time. I will take questions, but I think I'll let Neelavo start off. If we have time at the end, right near 7:30 or so, then we'll take the questions. Okay. Sorry, I think I've exceeded the time a little bit, but I hope you have enjoyed this part of the session. Neelava will just be continuing on how PyTorch is going to be very, very helpful in reducing the complexity of our code. So, okay, I'll hand it over to Neelavo. So,
yeah, I think I will also try to make sure we have time for doubts and some extra stuff
great,
that I have planned in the end. Thanks, Atreya. Hi, my name is Neelavo, and I will just start screen sharing and take you guys through what PyTorch is and building a neural network with
Yeah,
PyTorch.
Neelavo, I guess we can give them 2 minutes time to take a small break, and then we'll start at 6:30. That should be better.
Cool.
And also, guys, the notebook for the NumPy implementation and all the remaining content has been posted already on the GitHub, and also we'll be sharing after the session. So don't get intimidated by the code. We just wanted to show you that implementing a large neural network model using NumPy is definitely difficult and painful. And now we'll be understanding the power of deep learning frameworks like PyTorch. So Neelavo will be explaining that. So you'll realize that by using frameworks like PyTorch, you need not get into the math part. Like if you see the NumPy implementation, for example, you have to hard code everything, including the derivatives, the back propagation steps, everything altogether, which takes a lot of time. But in PyTorch, you have facilities like just using dot backward, which makes your life a lot more easier. So we'll be diving into that and we'll be getting a better idea of PyTorch in general. And also we'll be implementing the same NumPy model that you have seen using PyTorch. And that'll give you a much better idea and you'll be able to appreciate deep learning frameworks much more after seeing that. So you'll be able to code that huge NumPy implementation within just 5 to 6 cells and without hard coding anything and doing it in a much more elegant and easier manner. Saying that, I guess we can start right now. Neelavo, you can begin.
Yeah, so intro to PyTorch and building neural networks with it. We'll get the ball rolling with what is PyTorch, also why are we using it. Uh, PyTorch is a machine learning framework. What that is essentially it's an interface or a library or a tool which allows developers to more easily and quickly build machine learning models. And we don't have to, as Ritvik and Atreya stated before, we don't have to get into the nitty gritty of the underlying algorithms. We don't have to hard code a lot of it because a lot of okay, once researchers figured out that linear neural networks are a thing and they work in a particular way, uh, having to code that again and again is a huge pain. So they, let's say they want to use that as a component in a larger algorithm, then they can just use PyTorch and code that a lot more quickly, so they don't have to waste time doing it every single time. But before we get to why we use PyTorch, this is a Slido poll link. I'd like to have you guys scan this and I want to know what you think on why we use PyTorch and machine learning frameworks. This is the Slido link. I'll start the quiz. I'm just gonna wait till the number of participants saturate a little bit. Okay, I think you guys can keep joining. I will just display the question, and again, as the answers come in, I'll move on to the correct answer. But this is really just to gauge or like to see what your intuition about a machine learning framework is from all that you've learned today. I'll just read through the question while we're waiting. Why do you think we use machine learning frameworks? Option A, they allow us to not have to do all the math necessary for any ML algorithm. I think Atreya covered this quite in depth when he showed you all the massive differential equations you'd have to compute. Option B, they allow us to easily implement optimizers and loss functions. We'll get into what those words mean. I think you know what a loss function is, but you should have a rough idea for what that is. Option C, they allow us to have to not manually code out well-known components of ML architectures. I may have just spoken about this. Option D is they are optimized to perform ML-related tasks faster. And option E is all of the above. I think most of you have answered this, so we'll move. And somewhat unsurprisingly, it is actually all of the above. And I think even if you don't know much machine learning, this is a decent guess because all of these are really cool things that we'd like our algorithm and our networks to be able to do. Okay, we have Bruh, who's answered it in 8 seconds, and then we have the top 5. Good job, guys. So we'll head back, and I'll actually be telling you why we use PyTorch. This, by the way, is the PyTorch documentation. So if you go to PyTorch on the internet, this is essentially what you'll see. I will be explaining to you what the documentation is and how you can use it shortly. So first things first, PyTorch is Pythonic, which means the syntax and the more or less the way it works and the logic behind it is very similar to Python. So if you know Python, PyTorch is already extremely easy to learn. Other than this, also like the way if you've been like learning Python syntax, if you learned Python for the first time through our session, you know that Python syntax is very much like written English. It's quite simple to understand. There's not much There's not much abstract like language. And so if PyTorch is similar to Python, that means PyTorch by extension is also really simple to understand and is really easy to learn. Also, PyTorch, since it's similar to Python and Pythonic in nature, you can use debuggers like PyCharm, which normally work on your all other Python code, and you don't have to have a separate debugger for PyTorch. Next, we have the fact that PyTorch supports dynamic computational graphs. This is a really fancy word, and we won't really get into what this is. But essentially, what this means is you can change the network behavior, or you can change the way your neural network is working while it's running. Why is this a big deal? Because in machine learning, to achieve like reasonable results, we use massive amounts of data, right? We use like thousands and thousands of samples for, let's say, even to teach a computer how to identify a t-shirt in a photo. We use thousands and thousands of samples, and let's say we have started the training and we notice something is off, or like we'd like to make a change, or let's say we're like 30% in. It's and we can see that we can make a small change to the network behavior and it will perform better. We can do that in experiment while it is running instead of having to stop it, make our changes, and start it all over again and wait till the end to make changes again. That's really inefficient. And so a lot of other machine learning frameworks require you to treat your model as a static object, and you have to define how it works before it starts, and you can only change it after it's done running. And the last point is that PyTorch has an organized open source documentation. So what this is, and I'll quickly show you what documentation looks like, is any class or any method, any function in PyTorch, you can go look up the documentation, or you can basically, let's say you wanted to look up nn.linear in PyTorch. Your top result is the PyTorch documentation, and you can go on it and it'll tell you all you want to know about it, how to use it, what parameters it takes, what it means, what it does. And the open source part is essentially you can access the source code for any given such function, and you can, it's I think pretty decently explained, and you can make changes yourself if you want to change how this function in PyTorch behaves. So that's really helpful for extremely advanced use cases where you would like to know exactly how this works and you'd like to make changes according to your own use cases. Okay, so now that we also, PyTorch has a really active and helpful community. This is good because you will eventually, at some point, you'll get stuck using PyTorch. Some function is not behaving how it should, etc., etc. You have a really nice and active open source community that'll help you out. In fact, the PyTorch website itself has like a community page. You can make an account and post questions, and it's fairly active. We'll be moving on to what the tensor is. The tensor is the central component or the central data structure that we use in PyTorch. They're very similar to n-dimensional arrays. In fact, like just purely what they are is they are n-dimensional arrays. You can see, as you should already know at this point, this is just a rank 0 tensor is one value, a rank 1 is one series of values, a rank 2 is a matrix, so you have 2 cross 2, or you have how many ever cross how many ever values. Rank 3 is a volume, and rank 4 is a collection of volumes. But yeah, you should already know what n-dimensional array is, and that's basically what a tensor is. But what makes our tensor better or different from an n-dimensional array is that it's optimized for machine learning. So there's two major optimizations. First is that tensors are CUDA compatible, and they are built to run on hardware accelerators like GPUs. Why this is important is, again, in machine learning, you will have to run vast amounts of data and for like meaningful higher level models. And any hardware accelerators and GPUs you can use are always welcome, and stuff you will be requiring to run through this data faster. And tensors are just optimized to run this way. CUDA is a service by NVIDIA, which allows you to make use of your GPU and graphics cards better using parallel computing. That's not something we're going to get into. But it basically allows you to work a lot faster. And so the vast amount of data, features, training, iterations, etc., are like compute in far better times using the architecture of GPUs and other hardware accelerators. The other important optimization is that tensors possess is that they are optimized for automatic differentiation, which is essentially every time you use tensors in everything that you do, they're optimized, and you expect like the machine is expecting them to be used for differentiation, and they're optimized for that. And you might have seen in the basis of backpropagation, which is a lot of machine learning, uh, is this ability to calculate derivatives precisely. And so this optimization really allows us to speed up again how our network is working, because the derivatives are automatically computed very precisely and fast. For those that are more interested in this, you can have a look at this article. If you just look up autograd or torch.autograd, you'll get this article, which essentially tells us how it's PyTorch's automatic differentiation engine, and it's very very useful. There's a nice YouTube video by 3Blue and Brown that explains this better. Okay, now we move on to nn.module, which is the heart of PyTorch. It's the base class used to develop all neural network models using PyTorch. And this is what allows you to easily make a linear neural network or a convolutionary neural network, also known as a CNN. And you can even combine them. This is actually the beauty of it, or what's really nice is that you can create such very very complex architectures, combining, let's say, some parts of like the convolutions of a CNN or something, and then at some point you run that through a fully connected neural network like this one here to finally get your classification. So like the possibilities of what you can do are limitless, and they can do them very very easily with PyTorch and nn.module. Today we'll be looking at developing a fully connected linear neural network. Looks something like this, but a lot simpler. We'll get into that a little bit later. Some things that we might want to just recap on, Atreya has told you about some of them, and will be useful for us, is number one, torch.device. Torch.device is usually what device you're doing all the computation on. We'll get into this when I do the code, but let's say the tensors that you store and the functions that you run or whatever the loops that you run, essentially where everything is getting computed. And because PyTorch is optimized for hardware accelerators and GPUs and whatnot, it's useful for you to specify which device you want to run it on. In fact, if you have a very elaborate setup and you have multiple GPUs, you can, with torch.device, specify which tensor is computed on which GPU, or which part of your code is computed on which GPU. And so that's really really nice. Your loss functions. Some loss functions are built into PyTorch, like your mean squared error or cross entropy loss, which we'll be looking at today. And essentially, this makes the doing the math or writing the loss function a lot easier. I'll look at that a little bit later as well. And torch.optin, this is a package that includes the implementation of optimization algorithms like ADAM and SGT. Again, Atreya very briefly touched on this, but we basically focused on gradient descent. Like gradient descent helps you get to the minimum loss or helps you minimize your loss. There's many such algorithms, like similar to gradient descent. Most of them are sort of inspired by it, that help you also reach the and minimize your loss, help you reach the minima of the loss function plot. And the most popular one is ADAM. There's also stochastic gradient descent. Each of them have their own pros and cons, why they are good, why they are bad, but we won't get into those today. You just need to know that there's more optimizers in the world than your gradient descent. Before we move on, actually, I will show you a little bit on tensors, because we'll be using them very extensively today. And so just to get you a little bit more comfortable with them, as always, we start with importing torch, and we may create tensors that I spoke about. In fact, let's go back to that slide. There we go. By using Python lists, if you're familiar with Python lists, which you should be after the first session. So you can define a list and just use torch.tensor of A, and you get a tensor. And when you print this, you see that Colab tells you that it is indeed a tensor. And this is important because, as we discussed, tensors have certain special properties, and you want to make sure your data is stored as tensors. You can also do them from NumPy arrays. Let's say you're comfortable, or you've got some part of your code written out in NumPy arrays, then again, very simply, just torch.tensor, and you put in the name of your NumPy array, and it will convert it into a tensor for you. You can also directly use the torch.tensor constructor. This is essentially what we did here, but instead of defining a Python list first and then converting it into a tensor, you can define it just the same as you would the Python list and just put that inside torch.tensor. Right. I mean, you guys can take a second to just see that these tensors are these like lists or NumPy arrays are accurately converted to tensors. If you would like to confirm that, and we're going to move into something also very important. That's the basic attributes of a tensor. So tensor, like arrays, store a single data type, right? And so dot data type, dot d type. So a tensor, which was this one here, we can see that it stores integers. So when we do a tensor dot d type, it tells us that it stores torch.int 64. This is basically 64-bit integers. Dot shape, it tells us the shape on this of the tensor. This is again similar to NumPy arrays. It basically tells us the dimensions. So if we go up here, we notice that this has 3 rows and 3 columns, and so the shape
Nilava?
or the size is 3 cross 3. Mm-hmm.
Yeah, can you zoom in a little?
Yeah. Okay.
Yeah,
I will just
this should work.
yeah. In case you were not able to see earlier, I'll just quickly go through the code. None of this is like particularly groundbreaking. And finally, dot device, which basically tells us what device the tensor is being computed on. So in this case, if you do a tensor dot device, it tells you that I'm doing it on my CPU and not a GPU or like enabling CUDA. This again is useful and is something that's sort of unique to tensors and PyTorch, because you can specify which device or GPU or which hardware accelerator of yours you want the tensor to compute on. Some useful ways to generate tensors. I think Atreya went over this, but a zero tensor is torch.zeros. Basically, you put in the dimension that you want, and it will generate a tensor of that dimension with just zeros. You can specify the data type. I think the default is float. And if you see here, I've added a requires grad is equal to true. You don't need to add this. And this is basically a parameter or something you can specify in any tensor that you define. And this comes back to our automatic differentiation and the fact that tensors are optimized for computing derivatives. So required grad is equal to true basically tells it that that this tensor will be useful in computing gradients later, and we should be able to find gradients with respect to, or like with basically involving this tensor. Notice also that it's ZEROS Americans. But yeah, that's torch.zeros, torch.ones, same thing. You just specify the dimension that will give you that tensor with ones. Over here also, I could have added requires grad is equal to true or false. That you can always do. But by default, you don't need to. It's not a necessary attribute. And torch.rand, which generates random numbers between 0 and 1. So here I've done a 3-dimensional tensor. As you can see, it's 4 2 cross 2 matrices, and they all are numbers between 0 and 1. But something I want to show you after this is the ability to reshape tensors. Now, I don't know, I mean, this might have been covered in a previous session, but we'll quickly go over it. Reshaping is basically, I don't want to lose this data, but I don't want it to be 3-dimensional anymore. So I could just combine this into a single row, right? And then I could combine these two into a single row. I could combine these two into a single row. I could combine these two into a single row. And then I would just have a 4 cross 4 matrix, because these would move up, these two would move up, these two would move. I would just have a 4 cross 4 matrix. Notice how I'm not losing any data here. I have the same amount of data points as before, but I've changed the shape to be a 2-dimensional array instead of 3-dimensional one. So one way of doing is you just do torch. You for your new tensor is whichever tensor you want dot reshape, and you specify what dimensions you want to reshape it to. This -1 is a nice little feature where essentially you can specify which dimension you want to keep the same. So let's say this was a 4, 2, 2. I want to keep 4 the same. And if I add a -1 here, it compresses all of this to just be a single dimension. So it'll be 2 into 2, 4, which we see. We reshape it, print the reshape. We see torch.size is 4, 4, and it does exactly what we thought it would. It puts this next to this, puts these next to this, these next to this, these next to these, and makes it a 4 cross 4 matrix. But you might be wondering, well, you can't always like just specify any shape, and you're absolutely right. If you specify a shape, let's say 4 comma 3, you can't compress all of this data into a 4 cross 3 matrix without losing data. Like there are ways to do it. Let's say you define this and this have to be multiplied, this and this have to be multiplied, and then you do some definition of where you can compress this into a 4 cross 3 matrix, and only you know then how to uncompress it. But by default it can't do it without, I mean, just not interfering with any of the data. So it'll give you an error and it says you can't do this. If you put 4 comma 4, by the way, this should work. Yeah, and it'll give you the same tensor. Okay, so before we move on to actually building our neural network or going through the code, we'll quickly look at I'll show the attendance QR. So if you guys can scan it, I'll leave it up for like a minute. If you've already scanned earlier today, you don't have to do it again. But for those of you that haven't, this is your chance. By the way, guys, the Slido link I shared earlier, the QR code I shared earlier, you can post your questions there. I see no Q&A questions over there, but yeah, I'm reading those on the side. At the moment, there's no questions, but if you have any so far, you can just drop them in there. Okay, I think I'll just quickly look at the Slido. Well, if we make models that can learn to on their own, will thus not lose. Okay, this is more of a philosophical discussion than a technical discussion, and I don't, for what it's worth, I don't think it's true, and even if it is, it's really far into the future. Like so far, we're just building models, let's say, that are very specifically designed for one particular job. For instance, identifying a bike or a car, but I think it's a while before they basically start making models themselves and replace us entirely. But that's a more philosophical discussion for a later time. Right. So with this sorted, we will move on. I'll just show it for actually 10 more seconds in case anyone missed it. Okay. With this, we will move on to the actual code. And building a neural network using PyTorch. By the way, if you missed the attendance, don't worry. I'll show it once again at the end. I'll leave it on for quite some time then. We'll get started. Imports, as usual, we first just import all the libraries, everything we require. I'll quickly take you through it. To import PyTorch, that's just import torch. Torch Vision is essentially it contains all the computer vision related libraries and computer vision related methods for Torch. So essentially, what will help you work with images more. That's everything included in Torch Vision. Import torch.nn as nn. This is actually most of this is actually pretty standard in any neural network implementation you'll see. Mostly because we're lazy, so I don't have to write torch.nn every time. This is the nn.module that I talked about. So this contains nn.linear. This is for convolutional neural network, so 2D convolutions, batch normalization, loss functions. All of this we'll get into later. Torch.optim, this contains your optimization algorithms and optimizers like Atom, SGD, whatever. NN.functional, this you don't need to separately import this because you already imported torch.nn, but torch.nn.functional essentially contains a lot of useful functions that will, like your activation functions, etc. And I'm this is also imported as f just so I don't have to type this entire thing out. Torch.utils.data, from this you're importing the data loader. What the data loader is, and we'll get to in a second, but essentially it helps us manage data sets more easily. And why we need this is because when we start building like real world application, real world neural networks, we have a lot of data to deal with. And so it's this makes it a lot easier to manage and break it into batches, etc. And from torchvision.datasets, torchvision, by the way, it contains a lot of computer vision visual datasets like the one we'll be using today. So from there we import datasets from like the datasets included in that, we import that as datasets. Torchvision.transforms, this actually has this contains again a part of torchvision, but it contains all the things that help us like perform transformations on our data sets. So we import that as transforms, and then we import matplotlib as usual. So first I'd like to give you an overview of what we'll be doing today. As Atri has already spoken about, we'll be using the MINS dataset, which looks something like this. So what is this? This is essentially handwritten numbers in grayscale. What is grayscale is every pixel has just one value, basically telling it how dark it is. So it goes from 0 to 1, which is black to white. And the dataset contains images like this, and we have our model basically has to guess what number this is. So when at the end of my whole model completion training whatever, when I give my model this image, it should say 5, or when I give my model this image, it should say 9. Obviously all the numbers are not consistent. You'll notice one is written like this, one is written like this, one is written like this. These three ones are different, but all of them are ones. So my model is essentially learning how to recognize handwritten digits. Right. We will define first what a batch size is. So our batch size is, because we'll see in a moment that this data set, MNIST, has 60,000 samples, and that's a huge amount of data to run at once. And so we break it into batch sizes. We break it into batch sizes of 64. Like you can define whatever one you want. And this essentially is at once in our training phase in our model, we'll just like load 64 at a time. So that should sort of be easier to manage, and we just load it in batches. This is mostly just useful when we do the data loader, which I'll talk about in a second. First, we get our training dataset from datasets.mnist. Datasets was something we imported here from TorchVision. We have the root word dataset. Train is equal to true. This essentially tells us we'll be using this from this dataset. We'll be using this part to train. Transforms is equal to transforms.toTensor. Whatever this dataset is by default in. Let's say it was in NumPy arrays, we just convert it to tensors for our ease of use. And download is equal to true. Essentially, this dataset is automatically included in PyTorch with a lot of other datasets. This is particularly useful. Maybe I'll talk about this a little bit later. But in case you don't have it, download is equal to true makes it download onto your system. Test dataset is identical, but except it's just for the testing data. So train is equal to false. It knows that it's the testing data, and apart from that, it's identical. We define the train loader. The train loader is essentially a very useful data management tool, right? If it comes from your data loader, it's data loader with what data set you want to load and in what batch size you want to load. So in our case, this shuffle is equal to true false thing you don't really need to worry about at the moment, but essentially it's useful for when you're loading the data. If you shuffle the batches up and you shuffle the data in the batches when you do every iteration, that helps it learn a little bit better. That helps the model learn better. So basically every time it gives a batch, it doesn't show it in the same order. It doesn't really matter too much, but yeah, that's shuffle is equal to true. It improves the performance of the model. And we do the exact same thing for the test loader. Now note that again, for the test loader, we don't really care about whether it shuffles or not, and also it's not useful to load it in smaller batches to improve training, because the test loader, the model is just going to be run once on the test loader, and then we're going to see a testing accuracy. So if you'd like, you can make this like 2 times the batch size or whatever. You can basically load larger batches at once, and that's okay. Just run the cell. Understanding the data set. This is a very important part of any ML model building endeavor. You need to understand what kind of data set you have, and the sort of like how it's stored in your system, etc. So first things first, we figure out how many samples are there. Our trained data set has 60,000 and our testing has 10,000. This kind of makes sense. We need to have more training data, and then with like 10,000 data points in our testing set, we should be able to verify our results. And a general, not really a rule, but a general practice is, let's say you're given 100 data points and they're not like neatly segregated into train and test, as is quite simply done here with a simple train and false. You separate about 20% of it as testing and you keep 80% for training. But that's not something you have to worry about. So let's essentially look at now what is our training data set. So we'll look at test data set 0th index, which is basically the first sample in the data point. And this is what it outputs. It outputs a tensor and a number. So this is essentially this trained data set is a collection of tuples, and these tuples, each of them have 2 things in them, or 2 columns. It has one tensor and it has one number. Now, some of you may have a like preliminary idea of what this is, but let's just assume fine. We know it has a tensor and number. How do we proceed knowing this? So we print the shape of our tensor, and we find out it's 1, 28, 28. This has given us a slightly better idea. So we know this is supposed to in some way represent an image, and this is essentially how images are also represented in a lot of computers and a lot of computer science in general. Is they're represented as pixel by pixel values, as 2D arrays of just pixels, and ND arrays if you want to also represent the photos of the features of each pixel. So if we go through this, we see it's a 1, which is the grayscale value, 0 or 1, how intense, how white or how black each pixel is. And it's a 28 pixel by 28 cross 28 array or image. So you'll notice most of them are zeros, which correspond to black. So if you go back to the data set, you'll see that there's most of the, especially the sides and the corners, are indeed black in color. And then you have also, obviously, in the middle, you have some values. The closer you move to 1, the more white the image is. And you can just use matplotlib to quickly plot the first sample, which you see is a 5. It looks something like this. And you and me obviously immediately see it's a 5, but it's quite remarkable that by the end of this, we're going to also teach our computers to learn that this is a 5. This, by the way, not even a particularly good 5. It looks kind of like an S or whatever. So now we'll move over to building the actual model. So we'll be doing all of these things here. This is mostly so when you look at the notebook later, it's a little bit more organized. We set the device for our entire this thing. This is a very good habit, and you will see this in pretty much any ML implementation that you do or like you look at online. And it's essentially sets the device. As I told you earlier, you need to set the device because that's PyTorch allows you to basically compute different tensors and different functions on different devices. And in our case, and most cases, we'll just set one standard device and make sure everything is on that device. So device is equal to torch.device, CUDA, which is the NVIDIA service. So if CUDA is available, I mean, this again, this is why PyTorch is so easy to learn. This is essentially like what you read it to be as. It's not complicated at all. So the device is CUDA if torch.CUDA is available, and if that's not available, else you just use the CPU. So this is to make sure, by the way, in Google Colab, like CUDA is by default available, I think. So like if you set it, then you can make use of the CUDA that you can use in Google Colab. Input size is 784. Now you might be wondering where I got 784 from. That is the MINS dataset we just saw is 28 cross 28 pixel images. and where obviously will the first layer of our neural network will just input all these pixels. We'll give the network this entire image, every single pixel, and then from that we'll see what we do with it. Uh, and you might be wondering that, okay, but right now your input sizes are in, okay, not this here, r1 comma 28 comma 28 and not 1 comma 784, but that's something we'll deal with later. We'll reshape it during the data iteration. Number of classes is equal to 10. This is essentially, actually it's much easier for me to show you here. This is what our model architecture will look like. So we'll start at 784 neurons. For the sake of I didn't have enough space to represent 784 neurons. There's only a few of them that says 784 neurons. So this is, we'll put in all the pixels. We'll then pass it to another layer of 50 neurons. Why 50? This is entirely up to you, but in our use case, we'll do 50. What I'm essentially saying is out of these 784 neurons, it will be able to identify like 50 useful, especially useful pixels, or especially like one feature from these 50 neurons, or some features that is only about like in written handwriting, 50 useful features at best that it derives from these 784 neurons. So I don't think there's like more than 50. Obviously, this you can mess around with this in the code, and I'll show you how to in a second. But yeah, with our hidden layer will have 50 neurons. We will be ReLU activating the outputs here. I forgot to show the ReLU activation. And then finally, we'll have one layer. This is the only one that's true to size or true to scale. It has 10 output neurons, and each of them correspond to one of the 10 classes. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, that's our 10 digits. And so finally, when our model inputs, like outputs, we put in the image 784 value tensor, and it should spit out some values of these 10 neurons. And what we'll be doing is whichever has the highest value, we'll assume that our network is essentially saying it's that one. So it might give like 0.2, -1, -7. -7 is it really doesn't think it's a 2 or something. 0.7, 0.1, 0.2, 8, something like that. And so if let's say 8 or 3.2 or something is the highest is at 6, and that's the highest one, then we'll assume that our model is predicting that 6 is the right answer, or that the image that we gave it was a 6. So that's our model architecture. So number of classes makes sense, is 10. Learning rate we define to be 0.001. This is a hyperparameter, and you will have to learn to adjust this yourself. In fact, usually you do it by a little bit of trial and error. You define different learning rates, and you see how well your model is learning, how quickly it's learning, how good its accuracy is. And the number of epochs to be 3. Now, you should know what epochs are from a previous session, but it's okay if you don't. In our case, it's slightly different from what you've seen before. Because before we used to load all our data at once, but now since we're loading it in batches of 64, we realize that number of epochs, or like one epoch, is defined as when the model sees all the training data at one time. So it sees all 60,000 samples in batches of 64. So that's around like 936 or 937 batches. And it's once it sees all of this, that counts as one epoch. So when your model has seen all the training data once, that's one epoch. And we are defining it to run for 3 epochs. And now we get to the heart of PyTorch and n.module. And this from this point onwards, actually this entire session, like the code in general, might seem really intimidating, and I want to like make clear that it's not that bad, and you don't need to, I can't stress enough how much you don't need to remember all the syntax and all the nitty-gritties and understand what every single method does. Of course, with time, if you and it's probably good for you to understand what every method does, but you really don't need to. You can build excellent neural networks without understanding what every single little function or every single little class does. In fact, if you understand blocks of code, like just this entire block, what this does or what this entire block does, then you're sort of good to go, at least for this session. In fact, this is also a little bit complicated. I'll show you an even easier version here, which is the one we'll be using. But let's try to look at it. We use the inheritance concept here, which you learned in your introduction to Python in session 1. So we call the subclass nn.module, and we define our class neural network nn. We define the initialization method, which is the input size, the number of classes. The super constructor again comes through the concept of inheritance, and you would have learned this in the first session. And if you don't remember or you didn't attend the first session, it's okay. You don't have to worry about this. This is somewhat like a standard line of code that we add every time we use inheritance of a class. There's also like alternatives to this, but it's not worth getting into at the moment. So we define FC1 as nn.linear input size and 50. Now you might be wondering, what is nn.linear? Nn.linear, this is essentially what I'm defining is your first forward pass. nn.linear. What this takes is the input features, and essentially it tells you it takes a number of input features, number of output features. Again, that's defined very well here. In features here is size of each input sample, out feature, size of each output sample, and it takes whether it's a bias or not. Essentially what nn.linear does is when you give it some x, x which is your input data, it'll spit out y is equal to ax plus b, which a is your weights, b is your biases. There is an option, by the way, whether you want to include biases or not. So if you put bias is equal to false, or by default if you don't do anything, then I think it just spits out y is equal to ax. But if you want to add biases and do y, then you can do is equal to ax plus b. In my case, I've decided to do away with the biases, or like not specify them. That's also all right. It essentially only requires the input features and output features, and it does creates a single layer feed forward network with n inputs and m outputs. Let's say you do nn.linear nm. So over here, you take our input size 784 to 50. So our first feed forward would be from input size 784 neurons to 50 neurons. That's essentially what we define here. And then the second one is from 50 to the number of classes, which is 10. From 50 to 10, we define another forward passing. And now we actually go ahead and define the forward pass of this neural network, which Atreya has discussed earlier, what the forward pass is. And we'll be using this, obviously. So let's say this network is given x, which is your input data. This is obviously a tensor. What we do is first we use fc1 on x. So we pass x through its input size 784, which is expected input size, to 50. We use f dot ReLU, which is this is how it is to implement ReLU in PyTorch. You